Let's look at an interesting problem. We find a material for which the following curve is given. What can you tell about the material? So we find a material, we start with this, it's solid in this state, we give it heat, the temperature continues to rise, and then at a certain point, there's no temperature rise, it stays flat, and then we see that the solid seems to change a little bit, and then as we continue to heat it, again the temperature begins to rise. Then at a certain point there's no more rise in temperature. Even as you heat it, it stays flat, and we see that the solid has become a liquid, it's melted. And then the liquid, we see a rise in temperature, and then it flattens out again at a certain point. And then we see all the liquid has become vapor, and then it rises again. The vapor temperature rises as more heat is added. What can we say about this material? We can point to the temperatures at which phase changes occur. These flat regions are phase transitions. Here it changes from solid to solid, here it changes from solid to liquid, here it changes from liquid to vapor. What is the energy needed for each phase transition? For solid to solid, we can calculate that by looking at the delta H for the transition. For solid to liquid, we can calculate by looking at the energy required for this transition. Same way, from liquid to vapor, we can look at the energy required for this transition right here. If I wanted to use this material as a lubricant, what should be the temperature range of use? So as a lubricant, I would usually require a liquid state, so that when I put a stress on it, it flows and it resists that flow. I would probably use this region here. If I wanted to use this material as a soft solid, what would be the temperature range of use? In that case, it would be right here. I would look at temperatures between TAB and TBC. Let's look at a material with the same curve that we had seen earlier. We had seen that if I want to use this as a lubricant, this is the temperature range I should be looking at. If I want to use this material as a soft solid, this is the temperature range I should be looking at. Now, what are the heat capacities for the four phases? How can you calculate them? Well, we said that the heat capacity is the delta H divided by delta T for a unit mass. Since the x-axis is in units of calories per kg, it means that the delta heat here is given per kg, so we already have delta H per mass, and the y-axis is delta T. So the slope of the line is given by change in y-axis divided by x-axis, so that is delta T over delta H over m, so that's 1 over c. Hence the heat capacity of a solid A, so solid A here is 1 over slope of the line, 1 over slope of this line, so that's the heat capacity for phase A. Similarly, we could calculate the heat capacity of phase B, of liquid C, and vapors D by calculating 1 over the slopes of all of these lines. In all of these cases, notice though that the heat capacity is a constant. The slopes of these lines are constants. That need not be true all the time. This is a constant as a simplified case. In real cases, these heat capacities actually change. So for example, it could change this way, it could change this way. And in such cases, we would actually have to either calculate average heat capacities in these regimes or use a temperature dependent function to describe this heat capacity.